Hello, ladies and gentlemen. Thank you for coming to my talk. I'm a master's student. I study industrial engineering at Azad University in Iran. Thank you. First of all, let me thank the organizers, especially my dear friends, Professor Choi and Professor Yoon, who invited me to this workshop. Today, we want to talk about a new concept which was introduced by Professor Azad in previous year by the name of Z numbers. It's actually related to the natural language, and we can say it's a combination of probability and possibility in a natural language, and also uncertainty. In the first part, I will describe Z numbers and some related concepts such as Z valuation and Z plus number, and also Z minus number, and some advantages and disadvantages of using these concepts. And I applied this concept to my field, actually project management, and a practical method to determining the final project time, which is critical path method. I will show the calculation of calculating critical CPM, critical path method in crisp, fuzzy, and also Z numbers environments. And then we will see how we can convert a Z number to the regular fuzzy numbers. And finally, I will describe a model which is based on alpha odds, and we can use this approach to solve this problem like that. Definition of project management is planning, directing, and controlling resources to meet technical and cost and time constraints of the project in a certain time. And who is responsible for this purpose? Is project manager, and he or she should be able to contact with his or her team, and he actually deals with a lot of information and a lot of people. And this is this question is defined by Professor Azad, that how reliable are the numbers and the information which we deal with. We want to answer to this question in a situation that, for example, you are a project manager. You want to need some information to determine your project time. So, first part is introduction to the Z numbers. Z number is intended to provide a basis for computation with numbers which are not totally reliable. And this is a pair of two fuzzy numbers, A and B. And for simplicity, both of them are assumed to be trapezoidal or triangular fuzzy numbers. A plays the role of a fuzzy restriction, and the second component, B, is reliability of the first component. Here is noted that restriction, not constraint, because actually restriction has the more generality, has more greater generality than the constraint. And there are some examples here. For example, about 3 hours is A, and usually. About 100 meters and quite sure. So, we can say when A is probability distribution of X, we can say that restriction on X is A, or possibility. We can say, I said that it's a probability distribution of that. We can say that restriction of X is membership function of A. And here mu may be viewed as a constraint, and it means that which U satisfy this constraint. And when P is when X is a random variable, So the restriction on X is P, and its probability is equal to PU. So we have another concept, which is z-valuation. And you know that uncertain computation is a system of computation which is not computation of values. It's computation of the restriction of the variables. And we define the z-valuation in this form. And this is the variable, and again A is the restriction of that, and B is the reliability of this in this second component. We can, in a natural language, we can understand this component by answer to this question: how sure you are that X is A? For example, I'm quite sure that population of South Korea is about 50 million. The variable can be population of South Korea, and restriction of that in this sentence is about 50 million. And how sure you are that the population of South Korea is about 50 million? I'm quite sure. Another example is, usually it takes me about 2 hours to travel from Seoul to Daejeon. Variable is travel time by train. The constraint is about 2 hours. And how sure you are that this time? It's usually. In order to determine the membership function of that, we can find an answer to this question. To what degree does the number A fit your perception of A? For example, to what degree does the number of, for example, 28 million does your perception of 50 million? And this is the membership function of that. In a natural language, we deal with a lot of information which are expressed as a Z information, which is the collection of Z valuation. And they are, you can understand that, you can understand them from some rules. For example, if anticipated budget deficit about $2 million, very likely, then reduction in staff about 10%, very likely. Usually we deal with a lot of this information and a lot of these rules in a natural language every day. So, Professor Azad introduced another concept by the name of Z plus number. Why he says he's Z plus number? Because it's second number. I said that the first number is restriction, the first component is restriction, and again it plays the same role in the Z number. But here it's not reliability, it's probability distribution of a random number. And actually it gives us more information about a Z number. And the Z plus number may be expressed in these forms, which mu is the membership function of A. And an example for Z plus number is approximately 9 is restriction, and normal distribution with mean 9 and variance 2 is the probability distribution of a random number, which is a second component in Z plus number. Also, he introduced another concept, which is Z minus number, which the second component is restriction on the probability of A rather than on the probability measure of A. As an example, a box contains 20 black and white balls. A ball is picked at random. If the ball is white, I get approximately $10. If it is black, I lost approximately $20. And I'm not given enough time to count the number and white balls. But many perceptions is that most are white. In this case, most 20 is the probability of the winning approximately $10. We can show that in this form as a z minus number approximately 10 and most 20. And now we want to apply it to my major, industrial engineering, and one of its field, which is project management. And the CPM, as I said before, is a practical method for determining project time. And I will describe it very briefly in crisp situation, and then fuzzy environment, and then Z numbers. For drawing a network, project network, we need three elements. First of all is activities, and next is precedence. For example, we should determine that each activity has one or maybe two or three precedents, and in CPM we don't use overlap in the activities. And the last one is duration. Before starting the project, we should know and we should determine the duration for each activity and describe and define its description to the team member. So there are two kinds of drawing project network, RON and AOI. And first one, AON, is activity on the node, and the next one is activity on the branches. For each activity, we should determine earliest time and earliest finish time, and also latest start and latest finish time. These are necessary for calculating the time in a crisp environment. So if one activity has just one procedure, its earliest start time is equal to the next activity earliest finish time. It's in forward pass. We have two kind of passes for calculating this duration. And if there are some precedent more than one, we should use the maximum of that. For example, as you see, it's now the time of 0. This is activity A has a for example, 2 days duration, and its earliest start time is equal to 0. Because this is a procedure of that, and also here can be 0. So this activity will start and it will finish in 0 plus 3, which is 3 days. So it is its precedence. So the next activity will start at, for example, 3 days, and here it will finish in the 2 days, and the next activity C will start, earliest start is 2 days. And we can calculate all these values by the forward pass, which is earliest start and finishes time. We each calculate earliest start and finishes time. And in backward pass, there are some rules, and I will describe it in this figure. For example, when you follow these rules, you can find this value, which is 15 days, for example. In backward pass, you should follow mentioned rule. For example, it was 15 days. The latest finish time is 15 days minus 2 days, which is activity time of activity H. And this activity is just one precedence of activity H. So here we can use 30 days as its time. And for this one, we should use the minimum time, you know, because it has here, I mean, we should use the minimum time of 4 and 10 because there are two precedents for this activity. And by calculating all of the values, we can find the slack for each activity, which is latest start time minus earliest start time. I mean this part minus this part, or this value minus this value. And some activities which its slack value is equal to 0, they are named critical activities, and the path is named as a critical path. In this table you can see that slack here is is 0, and it is located in the critical path. So, and finally we can see here slack is equal to equal to 0. Here slack is equal to 0. Here slack is equal to 6, and it's not in the critical path. And this is the finally in crisp environment. It was proposed to use another method which is based on linear programming, and this is a variable between activity I and j. And suppose that we have a set of nodes and a set of arcs, and activity times are described as a fuzzy numbers. By solving this problem, we can find the critical path in these problems. So, as a numerical example, here we can model it in this form. Activity time between duration time between activity 1 and 2 is 5, and there it's 6, and for activity 1 and 2 and 1 and 3, we should just choose one path. So in fuzzy environment we can use mentioned rule as a maximum procedure for some activities which in the forward pass, and also in backward pass we should use the minimum of that. But in the crisp environment, this equation is always correct. And for using a fuzzy environment in the fuzzy environment, it's not always true. So it makes some problem in calculations. And we have to use another method which is based on linear programming. And by using this model, we can find duration time of project in a fuzzy environment. Actually, I work in a company which produce some cars, and we made some projects in Iran. And it's air intake turbo compressor system, which is now one of our current projects, and it's a practical project, and you see more than 500 activities we should determine its time, and the project managers are deal with a lot of information which are expressed as a z number, because they are as a usually it's uncertain, and experts' knowledge is expressed to z numbers. So what can be find total project time duration in when activity time are based on z numbers? The first one is can be converted to the z number, converted to the classical fuzzy numbers, and another one can be calculation with z numbers. This one is described in the paper of Professor Azad and Professor Yager. But some concepts such as what is the square root of two z numbers? What is the radical of two z numbers? There are some complex concepts which are not totally in these days proposed, and I use a converter method which converts z numbers to the classical fuzzy numbers. Here is some definition, and As I said, for in the Z numbers, we should consider A and B as a trapezoidal or triangular fuzzy numbers. And in the first step, we can convert second part, which was reliability, to the crisp number, and we name it as alpha. In the next part, we can add this weight to the second part, which is reliability. And we can denote it in this form by Z alpha in the fuzzy environment. So you see it's a Z number, simple Z number. It's for first component, and it's the second component. And it was a Z number, and after adding the weight, it will convert to this value. So we want to just again, it's not normal because it's in the alpha level, and we can convert to the irregular fuzzy number, convert the irregular fuzzy number to regular fuzzy number. We can use this value, and we can multiply this value to another values, and as you see, the previous model will be converted to the normal, again, fuzzy number. As a numerical example, this is the first component of a Z number, and it's the reliability of that, or we can show in as a Z number. We can convert the second part to the crisp number. Its density function of that can be 0.9, and we can add its weight to the second part. You know, here it was 1, and now it's 0.9. So by using step 3, this Z number can be converted to the new fuzzy number. So, and now it's fuzzy number, and we can use a model which is based on alpha cuts. There are some definition here. For example, we can use some different alpha cuts. We have central value on left and side and right. So the model, the fuzzy model, will be changed to the lower bound and the upper bound of new variables. So we can solve this problem by using dual simplex, which is mentioned here. And this is linear programming. It's for lower bound of each alpha cut, and it's for upper bound of each alpha cut. So it will be changed to the two simple linear programming, and by using this model we can find these critical paths. And I applied these Z numbers to my field, which was industrial engineering, and it has more capability to apply in, for example, economical engineering and statistical engineering, and too many fields in the engineering. And thank you for your attention.
Any comments?